Learning objectives. In this chapter, the user would learn the following in detail: ATM features, protocol architecture, virtual channel and virtual paths, ATM cells, structures at UNI and NNI, generic flow control, header error control, ATM services, CBR, VBR, UBR, ABR, ATM adaptation layers, AAL1, AAL2, AAL3, 4, AAL5. ATM traffic control, connection admission control, CAC. Usage parameter control, UPC, virtual scheduling algorithm. Continuous state leaky bucket algorithm. Traffic shaping. ATM features: fixed size cells 53 bytes, virtual circuit technology using hierarchical virtual circuits VP/VC, PHY physical layer processing delineates cells by frame structure, cell header error check. Support for multiple traffic classes by adaptation layer. Example: voice channels, data traffic. Elaborate signaling stack. Backwards compatible with respect to the telephone standards. Standards defined by ATM Forum. Organization of manufacturers, providers, users. ATM services. The ATM Forum has specified 5 service categories in relation to traffic management in an ATM network. These categories are: constant bit rate CBR, real-time variable bit rate RT-VBR, non-real-time variable bit rate NRT-VBR, unspecified bit rate, available bit rate ABR. Constant bit rate CBR. CBR traffic includes anything where a continuous stream of bits at a predefined constant rate is transported through the network. This service category is used for emulating circuit switching where the bit rate is constant. This might be voice, compressed or not, circuit emulation, say the transport unchanged of a T1 or E1 circuit, or some kind of video. Typically, you need both short transit delay and very low jitter in this service class. Real-time variable bitrate RT-VBR. The real-time VBR service category is intended for real-time applications, that is, those requiring tightly constrained delay and delay variation as would be appropriate for voice and video applications. RT-VBR connections are characterized in terms of a peak cell rate PCR, sustainable cell rate SCR, and maximum burst size MBS. Sources are expected to transmit at a rate that varies with time. Equivalently, the source can be described as bursty. Cells that are delayed beyond the value specified by MaxCTD are assumed to be of significantly reduced value to the application. Real-time VBR service may support statistically multiplexing of real-time sources. Non-real-time variable bitrate NRT-VBR. The non-real-time VBR service category is intended for non-real-time applications that have bursty traffic characteristics and which are characterized in terms of a PCR, SCR, and MBS. For those cells that are transferred within the traffic contract, the application expects a low cell loss ratio. Non-real-time VBR service may support statistical multiplexing of connections. No delay bounds are associated with this service category. This is again a guaranteed delivery service where transit delay and jitter are perhaps less important than in the NRT VBR case. An example here might be MPEG-2 encoded video distribution. In this case, the information may be being retrieved from a disk and be one-way TV distribution. A network transit delay of even a few seconds is not a problem here. But we do want guaranteed service because the loss of a cell in compressed video has quite a severe effect on the quality of the connection. Unspecified bitrate UBR. This service category is designed for those data applications that want to use any leftover capacity and are not sensitive to cell loss or delay. Such connections are not rejected on the basis of bandwidth shortage, that is, no connection admission control, and not policed for their usage behavior. During congestion, the cells are lost, but the sources are not expected to reduce their cell rate. Instead, these applications may have their own higher level cell loss recovery and retransmission mechanisms. The UBR service is for best effort delivery of data. It is also a way of allowing for proprietary internal network controls. A switch using its own non-standard internal flow controls should offer the service as UBR class. You send data on a UBR connection into the network, and if there is any congestion in any resource, then the network will throw your data away. In many cases, with appropriate end-to-end error recovery protocols, this may be quite acceptable. This should be workable for many, if not most, traditional data applications such as LAN emulation and IP transport. Available bitrate ABR. This service category is designed for normal data traffic such as file transfer and email. Although the standard does not require the cell transfer delay and cell loss ratio to be guaranteed, it is desirable for switches to minimize the delay and loss as much as possible. Depending upon the congestion state of the network, the source is required to control its rate. The users are allowed to declare a minimum cell rate MCR, which is guaranteed to the VC by the network. Those with higher MCR may be denied connection if sufficient bandwidth is not available. The concept of ABR is to offer a guaranteed delivery service with minimal cell loss to users who can tolerate a widely varying throughput rate. The idea is to use whatever bandwidth is available in the running network after other traffic utilizing guaranteed bandwidth services has been serviced. One statement of the primary goal of the ABR service is for the economical support of applications with vague requirements for throughputs and delays. In an operational network, there may be bandwidth allocated to a particular user, but in fact, going unused at this particular instant in time. Either by providing feedback from the network to the sender or by monitoring the network's behavior, ABR service can change the bit rate of the connection dynamically as network conditions change. The end user system must be able to obey the ABR protocol and to modify its sending rate accordingly. Mapping of various data types and ATM adaptation layers. Service class, constant bit rate CBR. Quality of service parameter. This class is used for emulating circuit switching. The cell rate is constant with time. CBR applications are quite sensitive to cell delay variation. Examples of applications that can use CBR are telephone traffic, that is N into 64 kbps, video conferencing, and television. ATM adaptation layers. AAL1. AAL1, a connection-oriented service, is suitable for handling constant bitrate sources, CBR, such as voice and video conferencing. AAL1 requires time synchronization between the source and the destination. For this reason, AAL1 depends on a medium such as SONET that supports clocking. The AAL1 process prepares a cell for transmission in 3 steps. First, synchronous sample. For example, 1 byte of data at a sampling rate of 200 microseconds are inserted into the payload field. Second, sequence number SN and sequence number protection SNP fields are added to provide information that the receiving AAL1 uses to verify that it has received cells in the correct order. Third, the remainder of the payload field is filled with enough single bytes to equal 48 bytes. Service class. Variable bit rate non-real time VBR NRT. Variable bit rate real time VBR RT. Quality of service parameter. This class allows users to send traffic at a rate that varies with time depending on the availability of user information. Statistical multiplexing is provided to make optimum use of network resources. Multimedia email is an example of VBR NRT. This class is similar to VBR NRT but is designed for applications that are sensitive to cell delay variation. Examples of real-time VBR are voice with speech activity detection SAD and interactive compressed video. ATM adaptation layers AAL2. The AAL2 process uses 44 bytes of the cell payload for user data and reserves 4 bytes of the payload to support the AAL2 processes. VBR traffic is characterized as either real-time VBR RT or as non-real-time VBR NRT. AAL2 supports both types of VBR traffic. Service class. Connection-oriented packet transfer or available bitrate ABR. Connection-less data transfer or unspecified bitrate UBR. Quality of service parameter. This class of ATM services provides rate-based flow control and is aimed at data traffic such as file transfer and email. Although the standard does not require the cell transfer delay and cell loss ratio to be guaranteed or minimized, it is desirable for switches to minimize delay and loss as much as possible. Depending upon the state of congestion in the network, the source is required to control its rate. The users are allowed to declare a minimum cell rate which is guaranteed to the connection by the network. This class is the catch-all other class and is widely used today for TCP/IP. ATM adaptation layers AAL 3x4, both connection-oriented and connection-less data. AAL 3x4 prepares a cell for transmission in 4 steps. First, the convergence sublayer CS creates a protocol data unit PDU by prepending a beginning end tag header to the frame and appending a length field as a trailer. Second, the segmentation and reassembly SAR sublayer fragments the PDU and prepends a header to it. Then, the SAR sublayer appends a CRC10 trailer to each PDU fragment for error control. Finally, the completed SAR PDO becomes the payload field of an ATM cell to which the ATM layer prepends the standard ATM header. AAL5 AAL5 is the primary AAL for data and supports both connection-oriented and connection-less data. It is used to transfer most non-SMDS data such as classical IP over ATM and LAN emulation LAN. AAL5 also is known as the Simple and Efficient Adaptation Layer SEAL. ATM Traffic Control, Connection Admission Control CAC. Admission control is the simple practice of discriminating which traffic is admitted into a network in the first place. Admission control in ATM networks is known as Connection Admission Control CAC. Connection Admission Control is defined as the set of actions taken by the network during the call setup phase in order to determine whether a connection request can be accepted or should be rejected, or whether a request for reallocation can be accommodated. One method to avoid network congestion is to accept a new ATM connection during connection setup phase only when sufficient network resources are available to provide the acceptable QoS. This is called Connection Admission Control CAC, which is needed for connections where the QoS must be guaranteed. CAC establishes, modifies and terminates virtual path or channel connections. If the CAC is centralized, a single processing unit would receive signaling cells from the input modules, interpret them and perform admission decisions and resource allocation decisions for all the connections in the switch. CAC functions may be distributed to blocks of input modules where each CAC has a smaller number of input ports. This is much harder to implement but solves the connection control processing bottleneck problem for large switch sizes by dividing this job to be performed by parallel CACs. A lot of information must be communicated and coordinated among the various CACs. Some of the distributed CAC functions can also be distributed among output modules which can handle encapsulation of higher layer control information into outgoing signal cells. CAC is the set of actions taken by the network at the call setup phase or during call renegotiation phase in order to establish whether a virtual channel or virtual path connection can be accepted or rejected, or a request for reallocation can be accommodated. Routing is part of connection admission control actions. CAC is responsible for higher layer signaling protocols, signaling ATM adaptation layer AAL functions to interpret or generate signaling cells, interface with the signaling network, negotiation of traffic contracts with users requesting new VPCs or VCCs, renegotiation with users to change established VPCs and VCCs, allocation of switch resources for VPCs, VCCs, including route selections, admission rejection decisions for requested VPCs, VCCs, generation of UPC, NPC parameters, usage parameter control, UPC. While the CAC in ATXI networks decides acceptance and assigns network resources according to the source traffic descriptor values specified by the user at connection setup, usage parameter control forces the user to satisfy the specified values during the connection. Due to this, UPC function are sometimes called policing functions. UPC functions. UPC is defined as the set of actions taken by the network to monitor and control traffic. The main purpose is to protect network resources from malicious as well as unintentional misbehavior which can affect the QoS of other connections. Using parameter monitoring includes the following functions: checking the validity of VP1 and VCI to see if they are associated VCCs, monitoring the traffic entering the network from active VCCs, checking the validity of VP1 values to see if they are associated to active VPCs, monitoring the traffic entering the network from active VPCs. UPC locations. The UPC is located at the points where the VP or VC link connected to the user is terminated, that is, in the elements with virtual channel switching functions VCSW or virtual path switching functions VPSW. The three possibilities of location are: A. An user is connected directly to one VCSW. The UPC functions are performed in the VCSW on the VCCs before they are switched. B. An user is connected to one VCSW via VPSW. The UPC functions will be performed within the VCSW on the VICCs and VPSW on the VPCs only. An user is connected to another user or another network via VPSW. In this case, the UPC functions are performed within the VPSW on VPCs only, and the VCC usage parameter control will be performed by the first public network where one VCSW is present. UPC parameters. The parameters required to monitor and control may be the same as the ones used for source traffic characterization in the traffic contract: peak cell rate (PCR), sustainable cell rate (SCR), maximum burst size (MBS), minimum cell rate (MCR). UPC actions. At the cell level, different actions in the UPC can be included: cell passing, cell tagging, cell discarding. Cell tagging operates on CLP equal to 0 cells only by overwriting the CLP to 1. It is optional for both the network and the user. The user can set the CLP to 1 before the cells enter the network. If it is supported by the network, the user can select tagging during the traffic contract. Cells with CLP equal to 0 identified by the UPC functions as non-conforming to the CLP equal to 0 stream will be converted to CLP equal to 1 cells. These kinds of cells are called tagged cells. A tagged cell or a cell written by the end system as CLP equal to 1 if conforming to the CLP equal to 0 plus 1 cell stream is passed, otherwise it is discarded. By means of cell tagging, tagged cells can be transferred as long as they don't cause any serious harm to the network. If cell tagging is performed together with selective cell discard, tagged cells non-conforming to the CLP equal to 0 cell stream, or those submitted by an N system with CLP equal to 1 will be the first to be discarded at a congested element in case of congestion in the network. Therefore, CLP equal to 0 cells will be protected as much as possible. UPC algorithms. Although traffic conformance is defined in terms of the generic seal rate algorithm GCRA, the network is not required to use this algorithm for the UPC. It may implement the GCRA or one or more equivalent algorithms to enforce conformance. The GCRA is a virtual scheduling algorithm or a leaky bucket algorithm. Virtual scheduling algorithm VSA. The actual arrival time T of n is compared with the theoretical arrival time TAT, which is the expected arrival time under the assumption that the cells are spaced equally in time with distance I. The algorithm is intended to ensure that the average cell rate is not greater than I power minus 1, with some tolerance dependent on Z. This is, cells arriving later than TAT will be accepted, but cells arriving earlier than TAT will be conforming if T of n greater than or equal to TAT of n minus L. Otherwise, it will be non-conforming. The TAT value for the next cell is calculated as a function of T of n. There are three different situations. A. The cell is conforming. It arrives later than what is expected, and TAT of n plus 1 is equal to T of n plus I. B. The cell is also conforming, although it arrives earlier than expected. TAT is calculated as TAT of n plus 1 is equal to TAT of n plus I. The cell is non-conforming. It arrives too early. T of n less than TAT of n minus L. In this case, TAT is not updated. Leaky bucket algorithm LBA gives exactly the same results as VSA, but it is formulated in terms of capacity and content of one bucket. Figure: basic leaky bucket algorithm. The bucket is filled with the increment I for each conforming cell arrived, and it drains continuously 1 per unit of time. The maximum capacity of the bucket is L. When one cell arrives, it is accepted if there is space enough in the bucket for it. This is, if the content of the bucket after incrementing it in I is less than the maximum capacity Z. When the nth cell arrives, the content of the bucket is calculated as follows. Content n plus 1 is equal to content of n T of n plus 1 minus T of n, where T of n minus 1 minus T of n is the time passed between the nth and n plus 1 cell arrival, and it is the amount leaked by the bucket since the leak rate is 1 per unit of time. Conformance definitions for CBR and VBR service categories. NS percentage means not specified. NA means not applicable. The conformance definition defines conformity according to one or more GCRA. Therefore, different leaky bucket algorithms can be implemented at the UPC for controlling and monitoring the traffic. In ATM forum, different conformance definitions are given for the CBR and VBR service categories. For the CBR service only, one bucket is specified for the CLP is equal to 0 plus 1 cell stream. For VBR service, three possibilities are given, everyone with two buckets. In below figure, the difference between the C and D cases is that in the D case, tagging option is active. A CLP is equal to 0 cell that is not conforming to GCRA TS0, BT0 plus CDVT power 1, but is conforming to GCRA T0 plus 1, CDVT will have its CLP bit changed to 1 and it is said to be conforming to the connection traffic descriptor. Different possible situations in leaky bucket algorithm. Adaptation layers. ATM adaptation layer. The ATM adaptation layer AAL translates between the large service data units SDUs, for example video streams and data packets, of upper layer processes and ATM cells. Specifically, the ATM adaptation layer AAL receives packets from upper level protocols and breaks them into the 48 byte segments that form the payload field of an ATM cell. The ATM adaptation layer AAL interfaces the higher layer protocols to the ATM layer. It relays ATM cells both from the upper layers to the ATM layer and vice versa. When relaying information received from the higher layers to the ATM layer, the AAL segments the data into ATM cells. When relaying information received from the ATM layer to the higher layers, the AAL must take the cells and reassemble the payloads into a format that the higher layers can understand. This is called segmentation and reassembly SAR. 4 types of AALs were proposed, each supporting a different type of traffic or service expected to be used on ATM networks. AAL1. AAL1 was designed to support constant bitrate applications. It is appropriate for transporting telephone traffic and uncompressed video traffic. It requires timing synchronization between the source and destination and, for that reason, depends on a media that supports clocking such as SONET. The standards for supporting clock recovery are currently being defined. The AAL1 process prepares a cell for transmission in 3 steps. 1. Synchronous samples are inserted into the payload field. 2. Sequence number SN and sequence number protection SNP fields are added to provide information that the receiving AAL1 uses to verify that it has received cells in the correct order. 3. The remainder of the payload field is filled with enough single bytes to equal 48 bytes. AAL1 cell preparation. AAL2. AAL2 was initially conceived to support variable bitrate applications that require a bounded delay for delivery. One example of such applications is compressed packetized voice or video. The requirement on bounded delay for delivery is necessary for the receiver to reconstruct the original uncompressed voice or video. Although AAL2 was conceived in early years of ATM development, it was not designed. So later, when ATM designers needed a AAL for voice traffic, they first labeled it AAL6 and then quickly relabeled it as AAL2. So today, AAL2 is used for carrying voice traffic and allows several small compressed voice packets to be packed in a single 48 byte cell payload. AAL 3x4. AAL 3x4 supports both connection-oriented and connectionless data. It was designed for network service providers and is closely aligned with Switched Multi-Megabit Data Service (SMDS). AAL 3x4 is used to transmit SMDS packets over an ATM network. AAL 3x4 prepares a cell for transmission in 4 steps. 1. The convergence sublayer CS creates a protocol data unit PDU by prepending a beginning end tag header to the frame and appending a length field as a trailer. 2. The segmentation and reassembly SAR sublayer fragments the PDU and prepends a header to it. 3. Then the SAR sublayer appends a CRC10 trailer to each PDU fragment for error control. 4. Finally, the completed SAR PDU becomes the payload field of an ATM cell to which the ATM layer prepends the standard ATM header. The segmentation and reassembly SAR sublayer fragments the PDU and prepends to each PDU fragment a header consisting of the following fields. Type identifies whether the cell is the beginning of a message, continuation of a message, or end of a message. Sequence number identifies the order in which cells should be reassembled. Multiplexing identifier identifies cells from different traffic sources interleaved on the same virtual circuit connection VCC so that the correct cells are reassembled at the destination. SAR sublayer also appends a CRC10 trailer to each PDU fragment. The completed SAR PDU becomes the payload field of an ATM cell to which the ATM layer prepends the standard ATM header. AAL 3x4 cell preparation. AAL5. The convergence sublayer of AAL5 appends a variable length pad and a 8-byte trailer to a frame. The pad is long enough to ensure that the resulting PDU falls on the 48-byte boundary of the ATM cell. The trailer includes the length of the frame and a 32-bit CRC computed across the entire PDU, which allows AAL5 at the destination to detect bit errors and lost or cells that are out of sequence. Next, the segmentation and reassembly segments the CS PDU into 48-byte blocks. Then, the ATM layer places each block into the payload field of an ATM cell. For all cells except the last cell, a bit in the PT field is set to 0 to indicate that the cell is not the last cell in a series that represent a single frame. For the last cell, the bit in the PT field is set to 1. When the cell arrives at its destination, the ATM layer extracts the payload field from the cell. The SAR sublayer reassembles the CS PDU, and the CS uses the CRC and the length field to verify that the frame has been transmitted and reassembled correctly. AAL5 is the adaptation layer used to transfer most non-SMDS data such as classical IP over ATM and local area network LAN emulation. AAL5 cell preparation. Protocol architecture. ATM protocol architecture. The ATM protocol reference model is based on standards developed by the ITU. Communication from higher layers is adapted to the lower ATM defined layers, which in turn pass the information onto the physical layer for transmission over a selected physical medium. The protocol reference model is divided into three layers: the ATM adaptation layer AAL, the ATM layer, and the physical layer. The three management planes are user or control plane, layer management, and plane management. The ATM model consists of the following planes which span all layers. Control. This plane is responsible for generating and managing signaling requests. User. This plane is responsible for managing the transfer of data. Management. This plane contains two components. Layer management manages layer-specific functions, such as the detection of failures and protocol problems. Plane management manages and coordinates functions related to the complete system. Physical layer. The ATM physical layer controls transmission and receipt of bits on the physical medium. The ATM physical layer manages the medium-dependent transmission. It also keeps track of ATM cell boundaries and packages cells into the appropriate type of frame for the physical medium being used. Functions of the ATM physical layer. Cells are converted into a bit stream. The transmission and receipt of bits on the physical medium are controlled. ATM cell boundaries are tracked. Cells are packaged into the appropriate types of frames for the physical medium. The ATM physical layer is divided into two parts: the physical medium dependent PMD sublayer, the transmission convergence TC sublayer. The physical medium sublayer. The physical medium sublayer is responsible for sending and receiving a continuous flow of bits with associated timing information to synchronize transmission and reception. Because it includes only physical medium dependent functions, its specifications depends on the physical medium being used. ATM can use any physical medium capable of carrying ATM cells. Some existing standards that can carry ATM cells are SONET, Synchronous Optical Network, SDH, DS3E3, 100 Mbps Local Fiber, Fiber Distributed Data Interface FDDI physical layer, and 155 Mbps Local Fiber Channel physical layer. Various proposals for use over twisted pair wire are also under consideration. It specifies the physical media for the physical medium used, including connector types and cable. The transmission convergence sublayer. The transmission convergence sublayer is responsible for the following: cell delineation, maintains ATM cell boundaries, allowing devices to locate cells within a stream of bits. Header error control sequence generation and verification. Generates and checks the header error control code to ensure valid data. Cell rate decoupling. Inserts and suppresses idle, unassigned ATM cells to adapt the rate of valid ATM cells to the payload capacity of the transmission system. Transmission frame adaptation. Packages ATM cells into frames acceptable to the particular physical layer implementation. Transmission frame generation and recovery. Generates and maintains the appropriate physical layer frame structure. The ATM layer. The ATM layer provides routing, traffic management, switching and multiplexing services. The ATM layer provides an interface between the AAL and the physical layer. This layer is responsible for relaying cells from the AAL to the physical layer for transmission and from the physical layer to the AAL for use at the end systems. When it is inside an end system, the ATM layer receives a stream of cells from the physical layer and transmits cells with new data. When it is inside a switch, the ATM layer determines where the incoming cells should be forwarded to, modifies the corresponding connection identifiers, and forwards the cells to the next link. Moreover, it buffers incoming and outgoing cells and handles various traffic management functions such as cell loss priority marking, congestion indication, and generic flow control. It also monitors the transmission rate and conformance to the service contract. The fields in the ATM cell header defines the functionality of the ATM layer. The format of the header for ATM cells has two different forms. Use at the user to network interface UNI, use internal to the network, the network to node interface NNI. User to network interface UNI. ATM user network interface UNI signaling specification version 4.1 10,9 was standardized in 2002. At the UNI, the header dedicates 4 bits to a function called generic flow control GFC, which was originally designed to control the amount of traffic entering the network. This allows the UNI to limit the amount of data entering the network during periods of congestion. Network to node interface NNI. At the NNI, the header dictates 4 bits are allocated to the Virtual Pathfinder VPI. The payload type indicator PTI field is used to distinguish between cells carrying user data and cells containing control information. This allows control and signaling data to be transmitted on a different subchannel from user data and hence separation of user and control data. The following descriptions summarize the ATM cell header fields. Generic flow control GFC provides local functions such as identifying multiple stations that share a single ATM interface. This field is typically not used and is set to its default value of 0, binary 0000. Virtual Pathfinder VPI, in conjunction with the VCI, identifies the next destination of a cell as it passes through a series of ATM switches on the way to its destination. Virtual Channel Identifier VCI, in conjunction with the VPI, identifies the next destination of a cell as it passes through a series of ATM switches on the way to its destination. Payload Type Indicator PTI indicates in the first bit whether the cell contains user data or control data. If the cell contains user data, the bit is set to 0. If it contains control data, it is set to 1. The second bit indicates congestion. 0 is equal to no congestion, 1 is equal to congestion, and the third bit indicates whether the cell is the last in a series of cells that represent a single AAL5 frame. 1 is equal to last cell for the frame. Cell loss priority CLP indicates whether the cell should be discarded if it encounters extreme congestion as it moves through the network. If the CLP bit equals 1, the cell should be discarded in preference to cells with the CLP bit equal to 0. Header Error Control (HEC) calculates checksum only on the first 4 bytes of the header. HEC can correct a single bit error in these bytes, thereby preventing the cell rather than discarding it. Traffic shaping. Traffic shaping is a mechanism that alters the traffic characteristics of a stream of cells on a connection to ensure conformance to the traffic contract, maintaining, of course, cell sequence on the connection. The implementation of traffic shaping is optional for users and network operators. At the end system, if traffic shaping is not implemented, a cell flow may be non-conforming and the network cannot guarantee the promised QoS performance. At the network, this mechanism can be implemented in conjunction with UPC/NPC functions. Possible implementations of traffic shaping are peak cell rate reduction, burst length limiting, pace in time, and cell scheduling policy. Peak cell rate reduction can be achieved by operating at a peak cell rate less than in the traffic contract, and hence the risk of conformance violation is reduced. Burst length limiting in VBR sources consists of limiting the burst length to something less than the maximum burst size (MBS) in the traffic contract. Cells can be spaced at the end system and their departures can be scheduled in time such that traffic parameters will not be violated and the cell delay variation (CDV) will be minimized. Virtual channel and virtual paths. Virtual Path Identifier (VPI) and Virtual Channel Identifier (VCI). The Virtual Path Identifier (VPI) and the Virtual Channel Identifier (VCI) together form the routing field which associates each cell with a particular channel or circuit. Each VCI identifies a single flow channel. The VPI allows grouping of VCs with different VCIs that can be switched together as an entity. However, the VPIs and VCIs have significance only on the local link. The contents of the routing field will generally change as the cell traverses from link to link. For the UNI, the routing field contains 24 bits and thus the interface can support over 16 million concurrent sessions. At the NNI, the field contains 28 bits, allowing for over 268 million sessions to share a link within a subnet. The cell loss priority (CLP) bit provides the network with a selective discard capability within each VPI/VCI. ATM uses virtual paths and channels to logically divide the bandwidth of the transmission path. Transmission path. The transmission path consists of the physical cable connected to a particular port of an ATM switch. The cable has a defined bandwidth, such as 155 megabits per second for an optical carrier 3 (OC3) optical fiber link. Virtual path. The bandwidth of the transmission path is logically divided into separate virtual paths and identified using the VPI in the ATM header. Each virtual path is allocated a fixed amount of bandwidth. Virtual paths do not dynamically vary with bandwidths beyond what has been allocated. A virtual channel. The bandwidth of a virtual path is logically divided into separate virtual channels using a virtual channel identifier in the ATM header. Unlike virtual path, virtual channels share the bandwidth dynamically within a virtual path. Conclusion. In this chapter, we have covered the following in detail: ATM features, protocol architecture, virtual channel and virtual paths, ATM cells, structures at UNI and NNI, generic flow control, header error control, ATM services, CBR, VBR, UBR, ABR, ATM adaptation layers, AAL1, AAL2, AAL3, 4, AAL5. ATM traffic control, connection admission control, CAC. Usage parameter control, UPC, virtual scheduling algorithm. Continuous state leaky bucket algorithm, traffic shaping.